Hi everyone. So the next topic that we're going to investigate in the book is called the density of states. And this is a bit of an abstract concept. And so I like to start with some more concrete example in my class. So what we're going to look at is the idea of a Roman amphitheater. And we want to know basically how many people can we sit in this amphitheater here. So let's imagine that the benches are circular and that the amphitheater goes all the way around. And let's look down from the top. So looking from the top, we've got some inner diameter and then a bunch of concentric circles. If I could draw a nice circle, that would be nice. This is our radius. There's an inner radius A, and there's an outer radius B. So we're going to use an integral formulation to figure out how many people can sit here. So first off, let's figure out from the top, how much seating area is there? So the area of a circle is, sorry, I got ahead of myself, pi r squared. So the differential area at every radius, sort of the shell that represents one row of seating all the way around, is given by 2 pi r dr. And here you can see sort of this is the circumference of a circle multiplied by the thickness of a circular shell, which is the row thickness. So this is the total area, and if we want to know how many people we can fit in there, we need to know the area per person. So let's call that area per person, let's just give it a little factor. Since we're talking about Greek and Roman times, we'll call it theta. And this is the area per person. So we can define a function then that's the density of seats as a function of radius. We're just going to use g here, g of r. And this is going to be the differential area per row divided by the amount of bench space that one person takes up. So this is going to have units here of, well, let's look. So it's, let's say, meters squared divided by meters squared per person. These are going to cancel, and we're going to get people. If we integrate from A to B, we're going to get the number of people. So you can imagine in a large amphitheater this could be useful. Rather than really counting every single seat, you could make a count of the number of seats just by knowing the inner and outer radius of the amphitheater, and then doing some math here. So there's another there's another functionality that this can introduce. From the side view, obviously because everyone needs a good view of the stage, if we look from the side, the rows in this amphitheater actually gain height. So one nice thing about the density of seats function is that you can transform variables. So if you remember back to physics class, because we're sitting on Earth and there's gravity, the gravitational potential of each of these seats or rows of seats is just mgh. So m is the mass of the, let's say, the average person, g is the gravitational constant, and h is the height. So we could actually do an interesting thing here and transform the density of seats into the density of seats per gravitational energy instead of radius. So if we have one more function here, height as a function of radius, we can transform the gravitational potential into potential as a function of radius, and just by substituting in the h of r function. So for simplicity's sake, let's just imagine that there's no discretization here. It's a large enough stadium that we can say the step height is very small. Like there's only 2 inches between each seat, let's say, and so then the height as a function of radius is just some constant times radius. So we're essentially saying there's a linear slope to the seats. So then our v of r function becomes mg times this constant c times r. Okay. So now what we can do is recast the density of states function and I'm sorry, I just realized that I used the same symbol here. This is not the gravitational constant, this is the density of states, and I'm following the book on this one. So this is the density of seats. We're going to transform this into g of v. So we have v of r equals constant times r times the average mass per person times the gravitational constant here, and let's just wrap all this together into one big constant, and we'll call this lambda times r. So all this, and this just went into that lambda. Now our expression for g of r is 2 pi r dr over theta. So g of r equals 2 pi r over theta. So now we have lambda r equals v of r. So we can substitute in for r as v over lambda. And this is 2 pi over theta v over lambda equals our g of v. So now, instead of counting versus radius, we can count by height. We can say, well, how many seats are there as a function of height or gravitational potential, v. So if we want to count all the people, the total integral would be integral from a to b of g of v dv. And now up here again we have to figure out what dv is. So dv is lambda dr, and this is going to be equal to, now we have to remember that we're really counting in the integral, so we have to put a dr here and a dr here to get the total number of people. We would integrate both of these. we substitute in the dv here, and we get 2 pi v over theta lambda, and our dv is just sorry, our dr here, we have to change variables, is dv over lambda, and this also has to equal a to b g of r dr. Okay, so 2 pi r over theta is our g of r. So when we express that in terms of v, we get 2 pi over theta times v over lambda, check. When we express the dr, we get dv over lambda, check. So in the end, our total number of people that can fit in the stadium is equal to the integral from a to b 2 pi v over lambda theta squared dv. Now the last thing we have to do is transform these limits. So we have, the height at a, let's just call that 0. The gravitational potential v equals 0 at that point, and then let's just call this v max. So because the slope here is lambda, so we say we're going to set this equal to 0, and we're going to have our max height here is going to be h max is b times lambda plus a, and then this whole thing multiplied by mg for the gravitational constant is going to give us the Vmax. Okay, so we integrate from 0 to Vmax. If we carry out this integral, obviously there's going to be some cancellations, but the important thing is the integral of v by dv is v squared times some constant, and we're going to evaluate it from Vmax to 0. So we're going to get a finite integral. Eventually it'll come out to the number of people. Okay, I hope you could follow the concept at least. Instead of walking around the perimeter and counting each seat, we can stand in the center of this amphitheater, and knowing radiuses and how slopey the seating is, whether it's a steep slope or a shallow slope, we can count up how many people there are as a function of radius first, and then secondly count up how many people there are as a function of gravitational potential. Why you would want to do that, I'm not sure, but let's assume that there's some structural engineering reason for it. The point of this little exercise, though, is to make the real world analogy to the more abstract density of states which we'll encounter when we're trying to count up the allowed quantum states, that is, the allowed states that electrons can reside in inside the bands of a semiconductor, the semi-continuous bands on either side of the band gap where electrons can sit. So let's move on to that next.